Hi, Luca.
Can you see me?
Yeah, looks good.
Okay.
We'll go full screen and then go right ahead when you're ready.
Can you see everything?
Looks good.
Okay, great. Yes, so I want to give a report on the latest result on the SMEFiT interpretations within the SMEFiT toolbox that has been done in collaboration with several people, among which Etienne, Maltoni, Nocera, Rojo, Slade, and Vionidu and Sen. So I would like to start with by discussing what is SMEFiT. SMEFiT is a flexible EFT framework to do analysis in the EFT, and it has the built-in capability of producing a global EFT interpretation of particle physics data, including also non-LHC constraints. There are already some publications based on this framework. The first one that was produced was out a couple of years ago, and it was a top quark interpretation, an interpretation of the top quark sector. Then just recently, an analysis in the vector boson scattering and diboson sector has been produced, and Giacomo Magni is going to talk about it just in the next talk. And I'm going to focus on the combined EFT interpretation of the Higgs, electroweak, and top quark measurements at the LHC, which is in preparation at the moment. So this SMEFiT framework, this is a summary of it. And on the theoretical side, we have the standard model cross-sections have been computed with state-of-art calculations, mostly taken from the literature, some of them reproduced, including also next to leading order corrections, both in QCD or in electroweak. On the EFT side, we use the package SMEFiT NLO, which allows for NLO QCD corrections. And we computed both linear and quadratic contributions, and the latter can also be either included or excluded from the FIT, and we compare the two results. A brief word about the PDFs, which in order to avoid redundancy, we used PDFs in which no top quark data was used for the FIT, so that we don't have redundancy among the data sets. On the data perspective, as I said, we combine Higgs, top quark, and diboson production, including inclusive, differential, and simplified template cross-sections. And in terms of methodology, we have extended the framework with another fitting method with respect to the top quark only fit. Now there are two methods, Monte Carlo fit and nested sampling. I will briefly mention something about them later. And this framework has a modular structure, which means that it's very easy to add the new theory predictions and data and extend it for future analysis. The output of the framework. So first of all, we have a validation statistical toolbox, which allows us to get insights on our data set and on our sensitivities with things like Fisher information, principal component analysis, and so on. And then the major output is the posterior probabilities for the parameter, for the Wilson coefficients, which allows us then to determine the confidence level intervals. So just briefly, from the theory perspective, Maeve already talked about it a bit more in depth. We have the Lagrangian, which is the standard model Lagrangian, which is extended by a tower of higher dimensional operators. The first relevant corrections come at dimension 6 with a large number of operators and therefore of degrees of freedom. And if we want to get actually good sensitivities and break degeneracies, we need many observables and final state. And this is the point of doing combination of data sets in the FIT. The theory predictions for a generic observable are given by the standard model contribution plus a linear correction, which is the leading order 1, proportional to 1 over lambda squared, and then a quadratic correction, which can be included. And it's we're going to see some comparisons. It can be useful in many instances. So in terms of the operators, we included in the FIT, this is a table summarizing the degrees of freedom included. In total, we have around 50 operators. We have 50 operators from 4-quark operators to current operators and purely bosonic ones. Several of these, however, enter in electroweak precision observables, which we do not include explicitly in the FIT. So in order to take them into account, we decided to take the directions in the parameter space, which are here listed, and they are constrained by electroweak precision observables, and we decided to set them to 0. In this way, we remove from the FIT 14 degrees of freedom, and we end up with 36 independent coefficients. This is obviously just an approximation, which has is valid as far as the electroweak precision observables are. The constraints coming from there are way more powerful than the ones coming from the LHC, which might not be the case, especially in the future. So the next step is going to be, for us, is going to be to include them explicitly. But this is just the first step. The data that we have top quark production from TT bar to TT bar associated with an electroweak boson, single top, and 4 top productions for a total of 150 data points. On the Higgs production and decay side, we include run 1 and run 2 signal strength, as well as differential distributions and simplified template cross-section from run 2, and the boson productions both from LHC and LEP2, for a total of 317 independent data points. It is very insightful to look at information geometry, which is one of the validation tools we have in our framework. Fisher information allows us to get a feeling of how each data set is bringing constraining power to the coefficients. And for instance, here we have a heat map on the left, the linear, a table for the linear case, where we fit only the linear corrections, and on the right, when we fit also quadratic. And then for each coefficient, we have the effects of the different data sets. And when we have blue, it means that there is a high constraining power, orange, slightly lower constraining power, and so on. So for instance, if we have a look at a specific operator, as for example, the top Yukawa, we can see that most of the constraining power is coming from Higgs run 2 signal strength, and then some of it from run 1 and the differential cross sections. The 4-quark, the 4 fermion operators are all constrained by top quark data as expected, and mostly from TT bar. And the triple gauge coupling is only constrained by diboson data. We do not observe any drastic change of the picture when including the quadratic corrections. There are some slight changes, but overall the picture is more or less invariant. Before going into the full fit by allowing all the operators to change simultaneously, it is interesting to look at the individual log likelihood, where by individual I mean that only one operator is allowed to move and all the others are set to 0. Now, there are different situations that can be observed, especially since the theoretical calculations can be done at quadratic, including the quadratic corrections, and then the profile is a quartic curve. So for instance, the most simple situation is when you have a Gaussian profile, and this is the case for the operator OPG, for instance, where there is no ambiguity, there is one global minimum, and this means that we expect that no problem will be found in the global fit in principle, and we will be able to go to and find the global minimum. However, the situation might be more complicated. For instance, the triple gauge coupling operator has a structure which is non-Gaussian, and there are 2 minima, but one of it is actually at a higher value in the likelihood, which means that it's not the global minimum, and if we don't have problems in the fitting procedure, we should be able to get to the global one, and consequently be able to find the confidence level intervals without problems. However, there are more complicated situations in which we find a degenerate minima, and this might lead to disjoint intervals. And if the fitting procedure is not optimized well, might get stuck in the wrong minima, which is non-standard model-like in this case, for example. So in terms of methodology, we have the Monte Carlo fit, which works by generating Monte Carlo replicas to construct a probability distribution in the experimental data space, and then determine the HEFT coefficients replica by replica by minimizing the cost function. We introduced a new method here, which is nested sampling, in which it's a Bayesian method that does a mapping of the likelihood by sampling from the prior space to locate the maximum. Being a sampling method, it does not need any optimizer, and it builds the construct the posterior distribution at the end of the Wilson coefficients. We cross-validated these two methods. We saw that we find fairly compatible results. So for the rest, I'm going to show the results coming from the nested sampling method. Okay, so one of the first things we can look at in terms of the results is the chi-squared value of the data sets and of the overall data set. So both separated in terms of the various categories or the total one. So if we look at the total one, we see that there is no huge improvement. The standard model chi-squared is slightly bigger, but nothing, not too big. And in terms of the single data sets, sometimes we don't observe differences. For example, Higgs signal strengths are more or less the same, but in some other cases, we observe stronger differences, as is the case of TT bar, for instance. In terms of quadratic corrections or linear corrections, here we have the posterior distribution for some of the operators that I selected, in which these effects are actually quite big. For some operators, the sensitivity is already good enough to not have any difference, basically, from the quadratic and linear corrections. But for some of these, we see that at the linear level, for example, in the first row for these 4 fermion operators, the sensitivity is very mild at the linear level, and it increases dramatically once we get to when we include the quadratic corrections. In the lower one, we see that it can change even, I mean, in the linear case, we just have maybe one solution, and we don't see a disjoint interval, for instance. And when we add the quadratic corrections, we see a more complicated posterior distribution. So this is the results of the global fit, where in the top panel, we see the constraints, the 95% confidence level intervals on the various Wilson coefficients and the central value. And we see that the global picture is mostly compatibility with the standard model, apart for a couple of operators, which can be better seen in the lower plot, where we plot the residuals. So the distance from the standard model value in terms of the uncertainty. And we see that there are a couple of operators here, that these are 4 quark operators, too heavy, too light, which seem to be a bit far away from the standard model, while all the rest are within one sigma. It is interesting to discuss the dataset dependence, for instance, and in our framework, it's easy to compare and to decide which dataset to include in each fit. And here I'm just going to show 2 examples. So the first one on the top is a comparison between the global combined fit in blue and a fit in which only the top data is included in orange. The So what we see is that the Higgs is bringing information on a lot of new operators, which were not constrained at all by top data, and also an improvement in the confidence level intervals on the operators which are affecting both top and Higgs sector. It's a bit difficult to appreciate from this plot because it's in a logarithm scale, but sometimes the improvement is even can be a factor of 2 or slightly less, but it's appreciable. In the second plot, it's interesting to check whether the beam. So what we checked was we removed, the orange bars. We removed from the dataset the beams that probe energies above 1 TeV. This way we can check whether we have problems, for example, in the validity of the EFT. And one interesting thing that we observe actually is that the tension in those two operators with the standard model value actually disappears. So it might be that there are some problematic beams, and one might want to investigate more. Finally, I want to comment a bit on the theory dependence in terms of the next to leading order correction in QCD. We see, so here we see the results of the fit when you include them or when you don't include them. In blue, a leading order, and in orange, at next to leading order. And the posterior distribution for a couple of operators. So I think the take-home message, which we see that they change quite significantly. I think the take-home message is that they are important. They might have important effects. So it's worth including them, and it's worth checking whether they have effects, especially we noticed that they are very important in the top quark sector. So this brings me to my conclusion. SMEFiT is a novel and flexible framework for global EFT interpretation, which has already been successfully employed for top Higgs and the boson data. And there are several functionalities to cross-check and validate the results that we obtain. The new steps from the future will be to add new data, which is going to be not too complicated, given the modular structure of the framework, from BBS to Tevatron, electroweak precision observables, etc. Then to improve the theoretical calculations by maybe including RGEs and LOQCD effects and electroweak more in all the observables, and improve the fit methodology, since when you increase the number of operators, you might require a better efficiency, which is actually, for example, the nested sampling methodology doesn't quite scale well with with dimensionality. So with this, I thank you for listening.
Thanks, Luca. So do we have any questions from the conference room?
I don't see. Oh, I see one.
Yeah, thank you. I saw you actually include the measured Higgs signal strength and also the respective differential cross section in your fit, right? Would there be some sort of statistical correlation or overlap of these two inputs you have put in your fit?
No, when we include correlations, first of all. So when from the experimental papers, when they make available the correlations, we do include them, and then we actually remove. So for example, if a measurement has a total cross section and then some differential distribution, we remove redundancies by removing beams, for instance, from the fit, such that then we have all independent numbers.
Okay. If I may ask another quick question on the previous page. Yeah. On your previous, I think that's very interesting. But I realized that, for example, for some of the operators, changing from leading order to next leading order, you have actually a significant decrease of the constraint, right, or the interval. And also, for example, this C1 UT. Do you know what was the reason?
Yeah. So now specifically each of these operators, I'm not sure. What I can tell you is that what happens often is that some of these operators do not interfere, or better, the interference is suppressed with the standard model amplitude. But once you include next leading order corrections, then you get a more relevant interference term. So this changes the picture quite a lot. This does not happen in the Higgs sector, for instance, where the next leading order corrections just add some real corrections. They do not induce new sensitivities, basically.
Okay,
But,
thank you.
Okay.
All right, so let me know, Shongyong, if you got some more questions. From,
I don't see any more questions here.
All right, we got a couple of questions from Zoom. So Céline, if you want to go ahead.
Yes, I was wondering, because you mentioned at the beginning that you removed the top data from the PDF, but I'm assuming there are other LHE data inside the PDF. So are there any that actually, I guess they're not using Higgs data for the PDF, but I could imagine that maybe some boson goes in there.
Honestly, I'm not sure.
It might be just Treliang and no diboson, but I'm not sure.
Yes, I'm not sure as well, honestly.
Okay.
I think we checked this and
Well, that should be safe. Yeah.
Yeah.
Okay, good. Thanks.
I think we also have another talk later on in this session specifically about the PDFs. So perhaps
yes,
we'll be able to clear that up then. Okay, so finally we have Alejo.
Yes, thanks. Hi, Luca, and
Hi.
Thanks for a very nice talk. My question was regarding that you say that there are some coefficients where basically adding the quadratic piece doesn't change anything. So that means that the bound is basically driven by the linear piece of the fit. Can you identify which observables are the cause of that? Or in other words, can you identify which observables at LHC are already sensitive to the linear pieces?
On top of my head, now I don't remember exactly, but I think mostly like the signal strength from the Higgs. I think they. Well, wait. Let's just have a look here. Actually, here we can see a bit. No. Okay, no. There is a huge improvement in the Higgs, for instance, sector. So yeah, I'm not sure which.
But for example, CTP. So I guess that it comes from the Yukawa, right?
CTP, yeah.
And that doesn't change basically between linear and quadratic.
Yeah.
So
yeah. That's probably because gluon fusion.
If that is driven by the Yukawa, I guess that the Yukawa you can say already.
Yeah.
Sensitive to a linear. That is interesting, I guess. I mean, if it's not sensitive, you have to try to improve that observable to make it sensitive to a linear piece, right?
Yes.
I see. Okay, thanks.
Thank you, Alejo. Any final questions from either the room or online? Otherwise, I can say with great pleasure that we finished the first half of this session slightly ahead of time. So thank you again, Luca.
Thank you.
Now is the time for a short coffee break. I propose that we go for 20 minutes, and so we reconvene here at 9:20. I'm just about to post the link for the Wonder Room. If at least the speakers wouldn't mind joining me in there for a little chat, that would be nice. Yeah, for anyone else, you just got to click that link, and there's a few instructions to follow, as well as, the password is there to stop any uninvited people from showing up. So with that, I say that we reconvene at 9:20 my time, which is, well, I say 20 minutes, 20 past the hour, because I don't know what time it is everywhere else. So see you in 20 minutes. useful.
Yes, sure.
Okay,
yeah.
Looks great. Perfect. Actually, in fact, you can just leave it there if you want, and we'll start back again in a minute.
Okay.
Should make sure that the conference room is also ready. So yeah, Shangyong, if whenever you guys are done with the coffee break, you can let me know. And
yeah, we're back from the break.
You're back. Okay. Great. So let's start for the second half of this session, where we're going to get a little bit more information on the global picture, and then some more dedicated insight on how to maximize sensitivity to some of these operators in LHC data. So we start first with Giacomo Magni, who will tell us about another SMEFiT result looking at vector boson scattering and diboson data. So please go right ahead.
Okay, good morning, everybody, or good afternoon, and thank you for inviting me to this talk. Today, I would like to present you our results on the analysis on VBS data and diboson data from the LHC in the context of the standard model effective field theory. In particular, I'm going to show you another SMEFiT standalone study based on the publication we had in January with Jake Hattier, Raquel Gomez-Ambrosio, and Juan Rojo. Our goal here is to understand the interplay between the VBS data and the diboson data in a dimension 6 effective field theory study, and particular to try to do a quantitative analysis of the impact of the VBS data when doing a fit together with diboson data to constrain the Wilson coefficients. This study can be considered the first step towards the inclusion of VBS data in a global fit together with the Higgs, top, and diboson data, as in the talk we saw before. Let me recap a bit the theory settings that we have. We expand the standard model Lagrangian to include the linear dimension 6 operator from the worst of basis. We include only bosonics operators, since we are going to discuss about processes in which the electroweak bosons play a crucial role. And we do have a two fermions operator. They can modify the interaction between vector and the fermions, and we also have a purely bosonic operator modifying the interaction between boson themselves. And for instance, I'm going to point out that there is just one operator, CW, able to modify the triple and the quarti-gauge coupling, as you can see in the Feynman diagram. In particular, in VBS, there is also the possibility to access the quarti-gauge coupling, which is a unique feature of this process. And also, VBS can be mediated to an exchange of an Higgs field in a sort of T-channel, and those diagrams are the most interesting one when looking at the EFT effects. For the time being, we do not account for a quadratic term in our analysis, but we allow for CP violating operators, the one labeled with a tilde. In our analysis, we had 70 experimental data points split in 52 coming from the boson data, a fiducial and differential cross-section from Atlas and CMS run 2, and then 18 fiducial and differential cross-section from VBS, also from Atlas and CMS. All the vectors in all the channel are decaying leptonically. This is mainly due to experimental reasons, but of course we are open to analyze also other possibilities in the future. When there was a background, we simulated the EFT only in the signal region, and this is especially true for the VBS, in which we account for the EFT interference term only in the pure electroweak components of the measurements. In VBS is a process proportional to alpha electroweak at the power of 6 at leading order, in which you have 6 particles in the final states. Among them, there must be 4 leptons and 2 of them charged. And this characterized by the 2 jets with a huge separation in rapidity higher than, for example, 2.5, and a huge invariant mass higher than 100 of jets. This cut results in a low cross-section, which is around 1 femtobar in the fiducial phase space. On contrary, in the diboson production, jets are produced by QCD soft interactions, and so are modeled with Parton shower in our analysis. In diboson production, you also have 4 leptons in the final states, and you can select some cuts on the transverse momenta and the missing energy if you do have neutrinos in the final state. In this kind of processes, gluon fusion might be relevant to reconstruct properly the experimental measurement. In the slides on the right, you see 2 differential distribution, one from VBS on top and one from diboson, opposite sign WW, compared with the experimental results from data and CMS and our theoretical prediction. We start our theoretical calculation simulating some Monte Carlo events for the standard model with MADGRAPH and POECBOX at next to leading order. We then add the EFT linear contribution at leading order with a SMEFT sim UFO model, assuming as SU35 symmetry. We then perform Parton shower using PTI8 in order to model properly the jets, and we select the experimental phase space with a rivet analysis that we wrote specifically for each experimental dataset. Finally, we collect our experimental data from HEFT data with the corresponding uncertainties. Here, we show you some sensitivity plots in which we compare the standard model theory with the standard model plus the EFT, assuming that the Wilson coefficient has a reference value of 0.5. As you may expect, you can see that the EFT effects are bigger in the high tail of the distribution, but depending also on the process, you can have an effect in the bulk of the distribution, justifying that when you do such a fit of the Wilson coefficient, it's really important to include the differential cross-section compared to fiducial cross-section. Our fitting strategy is based on this toolkit called SMEFiT, which Luca just presented in the talk before. We define our figure of merit as a standard chi-square, and we include in our covariance matrix for all the experimental uncertainties and available correlation, and also for some theoretical uncertainties coming from the Monte Carlo and the PDFs. We then perform a Bayesian reweighting, sampling the posterior probability with an algorithm called nested sampling, assuming that we have a multi-Gaussian likelihood, which is proportional to the exponent of the minus chi-square, and a flat prior, which is assumed to be an hypercube in the space of the Wilson coefficient. The first quantity you might look in a fit is, of course, the chi-square. On average, we managed to reproduce our data set with a good accuracy also in the standard model hypothesis only. However, we observe some statistical fluctuation when looking at the VBS fiducial cross-section, and this might be due to the lack of statistics. So we expect that the chi-square will even improve when more VBS points will be, experimental points will be available. And then the chi-square is naturally reduced by the algorithm of minimization. Another interesting quantity to quantify the effect of each channel in a constraint one Wilson coefficient is the Fisher information, which is basically defined as the ratio of the standard model effective field theory contribution divided by the experimental uncertainties at the power of 2. In the table here, I show all the values for our 16 degrees of freedom, and you can see that the two fermions operator, which are the one listed in the top part of the table, are basically constrained from the diboson data. Instead, the VBS data start to play a role when you look at the purely bosonic operator, which are the one listed in the low part of the table. Here I want to stress that the constraint on CWWW, the operator modifying the triple and the quartic gauge coupling, are coming also in this work from the diboson data, and this is consistent with the previous talks. In this slide here, I show the posterior distribution, so the fit outcome for our baseline diboson plus VBS. On the left, you can see the posterior distribution of our 16 degrees of freedom. They all look Gaussian, so there are no flat direction, and this is expected from a linear fit. While on the right, you see 95 confidence level bounds and central values for 3 different scenarios. In blue, a fit including only diboson data, in orange, diboson plus VBS, and in green, the individual fits that you can obtain when fitting one Wilson coefficients at the time. Clearly, our constraints are coming mainly to the diboson data, but there is a small but consistent impact on the VBS from the VBS data, testifying that they do carry some additional information. Moreover, adding the VBS data to our analysis permits us to fit 2 additional coefficients which are not constrained by the diboson data, which are CPB and CPB tilde. A useful tool that you can use to deepen the understanding of the correlation between the Wilson coefficients are the 2-dimensional fits. And you see here some 95 confidence level bounds. And you can see how the ellipses from a different selection of data set, VBS and diboson, do not overlap completely, testifying that VBS data carry some slightly different information from the diboson. In particular, you can see the effect on the operator CPB, which is not constrained by the diboson. In order to deepen our understanding of our VBS fit, we try to hire our statistics, including also some detector level events. We could include only bins with high statistics, namely the one in which there were events higher than 30. And we include some 2 different data sets, one from CMS ZZ-JJ production, and the other one a Gamma and the Z production associated with 2 jets from Atlas, for a total of 15 more data points. This way, we managed to break the degeneracy that we were seeing on CPB and CPB tilde, as you can see in the posterior distribution. And you see that on average, this improved a lot our constraint coming from a VBS only fit, and all the Gaussian distribution shrinks to the central value, which is a consistent picture, and testify that what we are lacking in this study is basically the statistics on the VBS data. Finally, we performed a toy model for high luminosity LHC, in which we randomize our theoretical prediction, adding some Gaussian noise proportional to the systematic and statistical error that we assume will be there in high luminosity LHC, which is roughly the 50% of the systematic that we have right now, and 80% less than the statistical that we have right now. We assume the same LHC binning of the distribution that we used in the previous fits, and we simulated the 61 data points in electroweak VBS only, meaning that we assume that in the future we might be able to separate and disentangle completely the electroweak signal from the QCD background in a VBS measurement. On the right, you can see 3 different scenarios. In blue, the VBS only results from our fit. using the current data. In orange, our baseline diboson plus VBS, and in green, the result of this toy model. There is a huge impact going from blue to green, testifying that in the future, VBS measurements might be competitive in a dimension 6 EFT study, and may also challenge the accuracy that we see right now from the diboson data. In conclusion, with this analysis, we show that VBS data are complementary to the diboson data when looking at dimension 6 EFT operators, and we perform a quantitative fit comprehensive of all the experimental data on VBS available right now. Of course, this is just a first step, and there are a lot of approximation we would like to improve. From the theory side, we would like to add dimension 6 quadratic terms, which might be important also for theoretical reasons, such as the unitarity. We would like to add also some next to leading order effects in the EFT and compare with the dimension 8 operator, which are the most studied in literature so far on VBS, and perform a coherent expansion of the Lagrangian to the order of lambda to the -4. From the fit side, instead, we might add other channel, for instance, single boson production and electroweak precision observable. And in the future, we might be able also to study a rare effect as the polarized VBS, which is so far covered by statistical uncertainty. And for that, we would like to add the possibility of fit a Poissonian likelihood to model properly the low statistics distribution. Yeah. Thank you for your attention. And if you have any question.
Thank you, Giacomo, for that nice overview. So let's open the floor to the conference room for questions.
I have one question.
Yeah, thank you. And yeah, exactly on this page, you said future improvements. And at the last point, you said compare with the dimension 8 operators. So VBS process is a bit special, right? Contains the various diagrams, and dimension 8 could be, already from the part of the diagrams. Do you plan to combine dimension 6 quadratic term altogether with dimension 8 interference in your future study?
Yeah, our fit tool permit to do that because it's really powerful in this sense. You just need the theoretical prediction, which of course are not really are the most challenging stuff to obtain because the calculation are quite long for VBS. We saw that there was an improvement in MADGRAPH and there are a lot of operators to consider. So doing the calculation is the most challenging part for including dimension 6, dimension 8 and dimension 6 quadratic terms. But then from the fits code, we are okay, and we will be able to fit them together, we think.
Okay, thank you.
I don't see any other questions in the room.
Okay, what about from our online participants? Oh, yes, I see a hand from Mike.
Just a quick comment on what the speaker just said. In terms of the calculation has essentially been done for many of the vertices up to dimension 8 that feed into your predictions. There's just the 4 vector vertex where there's a little more work that needs to be done. But I think if you look at the fact that the dimension 8 operator basis has been defined, for example, in the paper by Chris Murphy, I think the theory side is actually at this point defined out to dimension 8 for this process. It's just a matter of it's not in code.
Okay. Yeah, Okay, that's cool, and we are looking for it. So.
Céline.
There was a measurement of VBS, but not to 2 boson, but to 1 boson. So VBS going to a Z, which was showing slight CP violating tendencies that have been used for discussing EFT contribution to those things. So since you're including those CP violating operators, I was wondering if there were any plan to introduce also this kind of data in which you have a VBS, but just 1 single Z boson produced. And that might be especially interesting for you CP violating operators.
Yes, this is definitely true. ZJJ or WJJ production is on top of our to-do list for the next updates. And of course, we are thinking about keeping the CP odd operator also in the future updates, because when you add the CP odd operator, you may also want to consider some specific observables, which are not just differential cross-section. So we are thinking on it, and we'll see. But for sure, single boson production with 2 or 1 jets will be included in the future.
Okay, thank you very much.
All right. If we don't have any final questions, let's thank Giacomo again, and we can move to the second talk of this session. We have now Cameron Voicey, who's going to tell us